What causes fireworks? Fireworks are the result of a chemical reaction between gunpowder and a mix of explosive chemicals called stars. The composition of the stars creates the color of the fireworks. Where these stars are situated in the gunpowder determines the shape of the fireworks. When the gunpowder is lit, it creates a large amount of heat energy. The heat energy created from those gunpowder is absorbed by the chemical in the star, specifically the electrons of those elements. They reach their excited state, which is then followed by the return of their ground state as they lose energy. The energy they lose becomes light energy, which is visible and seen as a certain color based on the element. This process is called luminescence and is the more common way colors are produced for fireworks. It is also the method of producing different colored light that we have studied.
So this is wavelength, frequency, and energy for our elements. For a yellow firework, the yellow light has a wavelength of 570 nanometers, which is 5.7 times 10 to the negative 7th power converted into meters. Divide the speed of light by the wavelength to get frequency, which is 5.26 times 10 to the 14th power hertz. Then to find the energy of a yellow firework, multiply this number by Planck's constant. The final number is 3.48 times 10 to the negative 19th joule. Red light has a wavelength of 700 nanometers. This is 7.0 times 10 to the negative 7 meters when converted. To calculate the frequency of the light, divide the speed of light 3.0 times 10 to the 8th meters per second by the wavelength. This gets a number of 1 times 10 to the 15 power hertz. To find the energy of the red light, multiply Planck's constant 6.63 times 10 to the negative 34 power joules by the frequency just calculated. To find that energy of the red fireworks is 6.63 times 10 to the negative 19 power joules. Blue light, so this is for a blue firework. Blue light has a wavelength of approximately 430 nanometers. This is 4.3 times 10 to the negative 7 meters. To find the frequency, divide the speed of light by the wavelength to get 6.97 times 10 to the 14 hertz. Then multiply by Planck's constant to get 4.63 times 10 to the negative 19 joules of energy.
So for our fireworks, we have three distinct colors. That's what differentiates our types. We have red fireworks, which is created by strontium carbonate. We have blue fireworks, which is created with copper chloride, and we have yellow fireworks, which is created with sodium nitrate. So for these elements, they're all combinations of elements, like strontium, like strontium carbonate is strontium, carbon, and oxygen. With heat energy, this combination creates the reaction resulting in the fireworks colors. However, as seen with the flame lab that we did, only the first in the series of elements is responsible for the distinct color of the fireworks. So for strontium carbonate, it would only be strontium that creates the red light energy. However, as emits the energy. However, therefore, the Bohr's models below only show the first elements. So we have the strontium Bohr's model, the copper Bohr's model, and the sodium Bohr's model. So with energy, strontium can only create red visible light, copper can only create blue visible light, and sodium can only create yellow visible light. This is because the electrons in the elements, they can only absorb and emit a certain amount of energy, and also when they absorb and emit energy, they're limited by the energy levels that they can go to. So in terms of absorption and emission, all of the chemicals involved go through those things. It's visibly seen in the sodium model. So with it, the yellow arrow over here represents absorption. So energy is absorbed. The electron absorbs energy. In this case, it's with the heat energy, and it goes to its excited state, going from energy level 2 to energy level 3. Then with emission, it loses the energy, which comes off as visible light energy. With sodium, it would be yellow, and it goes down to its ground state, back to energy level 2.